Good afternoon to you all. Welcome to this session on FOSS for Spatial DBMS. I am Kapil Oberai. I am the faculty with the Geoinformatics department at IIRS. So in this session, we'll briefly cover the few fundamentals, which are the introduction to the databases and the concept of DBMS, followed by understanding what is spatial DBMS and what are its characteristics. Later, we'll also talk about few of the examples under FOSS category on the spatial DBMS. And then we'll also discuss what are the steps that are involved in handling spatial data using such spatial DBMS, taking the example of Postgres and PostGIS as an open source alternative to the proprietary softwares. In this, we'll cover the few primers on the SQL or the structured query language, and also see some basic spatial queries, taking some example datasets. So database is a term that we use to describe a structured collection of related data. So data we know are the raw facts, but database is primarily a structured collection of related data. We won't call a pile of, let's say, sheets as a database unless it is organized in a structured manner containing the related data. Now that could be our paper based, that could also be the computer based. Just like we have a word processing software for handling our word processing task, similarly for managing the databases, we also required a software, and that is called as a DBMS. The full form is Database Management System, and it is defined as a software system that allows us the defining, constructing and manipulating of the databases for various applications. Now databases are part of our everyday life. A common example in a, let's say, academic system could be student information system, or let's say from the business perspective, like employee information system, or every time we are booking a ticket through for the train or the airline, we are somehow interacting with such database systems. Now, just like a GIS allows us to create or use the GIS applications for various purposes, similarly, DBMS also offers generic functionality related to database organization and data handling that we could use for various purposes. Now DBMS, we could broadly, the software type could be classified either as, let's say, the proprietary or under the open source. Now the DBMS offers various advantages compared to storing data in the terms of files. Now unlike files, in the database, it allows the flexibility of storing a large amount of data, including putting constraints we call as integrity constraints, provision for stored procedures, provision for concurrent access, rights management, backup and restore, ACID compliance, which is a very important integrity criteria when storing data, all out of box. Now compare this to a file where we are restricted by the size of the amount of data we can put into that files depending on the OS. Other thing is, it's difficult for the file to be shared across in among multiple users, because once the file is opened, then it will be locked and the other person can't let's say edit the file at the same time. But if you look at from the database perspective, is let's say in the case of a train reservation, suppose multiple people are able to book the tickets at same time. One more way of looking around the difference between a database and file will be the concept of putting the constraint. Now in all these constraints are somehow stored as a part of the database system, whereas these constraints, if we talk about from the files, are somehow hidden within the application program through which that the data is being manipulated. Whereas it is in the database case, these are available as a part of a metadata inside the DBMS system. DBMS also provide kinds of rights management wherein based on the different roles people could access the data. Therein it can avoid the redundancy of data which is very much there in the file system. So depending on the role different users can access the same data depending on the rights that they have got. In a typical academic system, for example, or for a student information system, the module coordinator will be able to enter the marks for the particular module, whereas the other user, let's say the students who have enrolled for that course, can only view the marks. Similarly, the administration will want to know how many students have enrolled for this batch compared to the previous years. So again, all see the same data, but again all see the same data, but depending on the role, they are able to access different parts of the system depending on the role they have been assigned. So all are given access to the same data. It depends on through which window or a view you are viewing or want to access the data. Now the DBMS system has also evolved as per the IT technology development has happened. So earlier we used to store data on the magnetic media, followed by the various non-spatial database models that we come across, like network, hierarchical, and relational, which is very popular model for organizing our data in forms of relations and the relationships between those. The relations, or we call it also call as tables. Followed by the object-oriented database systems, which allows the existing RDBMS system to be extended to support user-defined types. And in between the RDBMS and ODBMS, we also have the concept of object relation DBMS, wherein some of the object-oriented capabilities are added to the relation database systems, or the relations database systems are extended to also support the user-defined types, which are primarily the way mostly the spatial databases are being implemented or are made available to the end users. Now, since early 2000, with the large amount of data that is being generated, there is a various types of systems have come. One is a NoSQL system, and also there are big data frameworks has also come for handling the large amount of data. But in this session, we'll be discussing primarily the relations and the object relations kinds of systems. So the database systems are very important when we talk about managing the non-spatial data. But similarly, for the spatial data, we also know it is quite vast, and we need to have a system which allows us to organize our data nicely, getting all the advantages of a database, which are large data handling, let's say the concurrency control, backup, restore, maybe fine-tuning of the databases, the integrity constraints, and so on. Now, Gutting has given a definition of a spatial database systems. So please note that to qualify a database as a spatial database, it should qualify or satisfy the three characteristics. The first characteristic is that a spatial database system is a database system, which means the spatial database system has all the capabilities of the traditional database systems that is to be offered. Further, it also offers or extends or provides support for the spatial data types in its data model and also in the query language, which means a traditional database system will only allow to store basic types like number, text, date, and so on. But in the spatial database, we can also store the spatial data like points, lines, and polygons. The third characteristic is that it should also provide the support not only the storage of data, but also the processing or analysis of the data that is being stored. So at least the support for the indexing on the spatial data, and also the various kinds of functions that we can apply on the spatial data like joins, spatial relationship testing, and so on. And the important thing is that the data storage and management is very essential in any data manipulation system, whether we talk about the the spatial data system or the non-spatial. So if we are able to organize our data nicely and able to manage it, the first part is being taken care. Rest is building the interfaces on the top of it so that the end users could be served. So to qualify as a spatial database, the following characteristics has to be should be there, which is a spatial database system is a database system but should also offer the spatial support for spatial data types and also the spatial indexing and the support for various spatial functions that works on those spatial types. So not only the storage is important, but also the, let's say, the manipulation of that data that we are storing in the system is important. Now one more differentiation we can make why in the spatial database is that here we are talking both from the non-spatial as well as the spatial aspects are there. Unlike in a relation system where we can only store the non-spatial data. So this slide talks about how does a traditional DBMS is different from the spatial DBMS. So first, as I said, is the capability to handle and manipulate the spatial data, or that let's say the geometry type. But not only the support for storage, but also the availability of various kind of functions that you could access from the query language, which is in DBMS terms is called as an SQL or a structured query language, which is a declarative language which allows user to post queries to the database and retrieve the results. But in the case of the spatial database, it is extended to now to support the operations on the spatial type, which could be the distance calculations, which means the given the 2 points, we can calculate the distance between the 2 points. We should be able to perform some spatial analysis functions like buffer, or given two relations or two layers, we should be able to overlay them, convert from one coordinate system to another. Now the below figure will further clarify the difference between the standard DBMS vis-a-vis the spatial DBMS. So in the traditional DBMS, we have the basic type, which are character, integer, real, and date. Similarly, it also provides functions to work on those basic types, which means there is a function called lower, which takes a text and convert it to a lowercase, or a function like round, which takes a real number and then round it off to some degrees, some, let's say, precision values. On the text side, we have some text manipulation functions like substrings, which means given a series of or line of text or few characters, we should be able to extract a portion of it by giving the starting position and the ending position and the number of characters that we require. Again, those could be overloaded function, so we could have multiple parameters being passed. Similarly, there is a trim function which primarily removes the leading and the trailing white spaces. Now from the data type perspective, we have series of functions like given the date, we can find out the day of the week. But compare this to the spatial database, and from the definition, so the spatial database system will have all the capabilities from the database system, which means it supports these types or basic types, but it also now supports the spatial data type, which means the support for storing geometry, which could be point, line, and a polygon, and also the functions on those data types, which is, let's say, given a polygon, we should be able to get the area. So st underscore area, suppose this is a case of Postgres and PostGIS. Again, distance, given 2-point geometry, we should be able to, we can get the distance between the 2 points. Similarly, we can also check whether the two geometry intersects one another. So the spatial DBMS has all the capabilities of the traditional DBMS along with the support for the spatial data types. Now the question could be why we should use a spatial database when we already have a GIS system in place. From a GIS perspective, it allows us to handle both the spatial and the non-spatial data, along with providing a series of tools both from the raster and under the vector domain to the end users. But we have to also remember that the GIS are not a database system. However, they can be connected to a database system. The other thing to note is a GIS cannot efficiently manage the large quantities of data. In a traditional standalone GIS system, if you look closely, the GIS takes care of the handling of both the data aspects, which is spatial and non-spatial, along with providing of the tools as I just mentioned. And sometimes we are restricted with the types of tools or the capabilities that the GIS allows us to refer or access from the data that is stored and that is stored and managed by the GIS system, which means we are restricted by the kind of queries capability that the system is provided. So which means we can't write ad hoc query if the system does not allow you to such capabilities from the GIS system. Now, other thing that we also know that is that database system, and especially the spatial database systems, are catered to handle large amount of data. And in the previous slide, I mentioned about the advantages of a database system versus the files. So they allow us the storage of large data, support for indexing, support for security, along with the query capabilities using the SQL. So now what we could also do is we could separate or delegate the responsibility of managing our data through a spatial database systems and let GIS takes care of the part like loading of the data, editing of the data, visualization, mapping and analysis, whereas the storage and the other aspects is being handled by the database system. Because if we talk about let's say the files, like let's say the shape file which has a storage limit of 2 GB, then if you want to store more data, then we have to look for some other options. But we could also store our data in these spatial database systems which provide let's say potentially unlimited kind of storage where we can store large amount of data. So from a single user or a small data handling, it will not make much difference. But if you talk about from the enterprise environment where multiple people will be interested in data and want to access it, we do require these kind of systems so that the data could be efficiently managed and could be served to the end users. So instead of GIS taking care of the data management, that task could be delegated to the spatial database system which are developed for handling and managing such data, and relieve the task of GIS for primarily for loading, editing and visualization, because spatial database system will not give you a capability of visualizing or those capabilities, but it will give you the capability of storage and also security and querying capabilities that could be used. One other way of looking at is that once the data is separate from the GIS system, then other system can still connect to the database system and access the data. But if your data is being managed by the GIS system, then if other system in a let's say enterprise environment want to access the data, then they have to only go through the GIS system if they provide those kind of APIs or libraries to access the data. So that is another aspect that we can look into. Right. So having talked about the why we should use the DBMS, and I've also given you a difference between a file-based approach and a database approach. So the spatial database system can primarily serve as a backend. So they could power our customized desktop application. It could be mobile or it could be web-based applications. And further, it will also, you can develop using this a multi-user or an enterprise kind of GIS system wherein the data could be organized in a separate SDBMS, and then based on the different roles and rights, people can access different parts of the data. Because consider a organization with multiple departments, and then those departments will be responsible for a particular data that they are generating, or some may be given the role of editing, some may be given the role of verification of those data sets. Then so in the multi-user environment, so different roles could be created, and depending on the role, people could digitize, somebody can verify, run those editing checks, etc., all from the using the power of the SDBMS. So a spatial database system can also serve as a backend, let's say the engine or a spatial engine through which the customized applications, so that could be like your Python based application or some mobile based application where you can store the data on a centralized server or a distributed environment, that could also power your web based GIS applications, primarily in the form of a client and a server kind of an environment. So having talked about what is a database, the database management system, the definition of spatial database management system, and what are the characteristics, and how does it differs from a traditional DBMS. Now let's talk about some of the free and open source softwares that are available under the SDBMS category. So in the first lecture, you must be you are aware that there are various open source tools that are available both in the non-spatial and the spatial domain. So if I talk about, let's say, the non-spatial domain, the widely used OS is the Linux, then the Firefox is a very popular open source web browser, and then the Apache, PHP, Python is a widely used, let's say, the language for writing custom code that could be for either for the desktop or web or for other applications. Similarly, there are also database management systems softwares that are available under the FOSS. There are many. The popular ones are MySQL, Spatialite, and then Postgres with PostSys. So PostgreSQL is the normal relation DBMS system, and then if we add the extension of PostSys, then it becomes as a spatial extension. So in the coming slides, we'll discuss on those the free and open source softwares for spatial DBMS. So FOSS provides many advantage, which is avoiding the vendor lock-in. You don't need to pay for the cost or the license. The source code is available. You can customize it. It supports the open standard, and people can also customize to and then distribute across without worrying about the license agreement. Now from the GIS perspective, there are series of GIS softwares that are available, from the desktop to the mobile to the web. Again, there are various requirements for cataloging, some WebGIS toolkit for building your front UI part or a presentation layer, some related to your data management and processing. Similarly, there is also a category of softwares called as the spatial DBMS, wherein PostGIS along with Postgres, Spatialite along with SQLite, and MySQL are some of the examples that people use for storage as well as management of spatial data. So basically FOSS for the geospatial application provide a series of tools which are comparable to the proprietary softwares, both under the desktop environment, to the web environment, and also under the spatial DBMS. Let's first discuss on the Postgres and the PostGIS. So PostgreSQL, also called as Postgres, is a object relation database systems, and it is available on all the major operating systems like Linux, Windows, and so on. It is fully ACID compliant, which is a very important property. ACID stands for atomicity, consistency, isolation, and durability, and it supports the basic what called functionality required in the databases, which are support for primary key, foreign key, the concept of a joins, the concept of views, triggers, and the stored procedures. Further, it also supports, you can connect this as a backend. So any programming language, as I mentioned here, C, C++, Java, .NET, Python, you can connect to this use Postgres as a backend for storing your data. Now, one of the issues, especially when you talk about the open source software, is the lack of the proper documentation. So compared to the other, let's say the softwares, the Postgres has very exceptional documentation available, and even there are textbooks now also available on how to work and go about using these systems. So as I mentioned, Postgres is our normal relation database system, but if we add the PostGIS, which is called as an extender, so it is like a normal system, and then if I extend it with the capability for storing, managing the spatial data, that is we call as a spatial extension to the Postgres. So after we have enabled the extensions, now it allows us to store the geospatial data along with the queries onto those data sets, all using the declarative language called as the SQL or structured query language. So Postgres has been around for a long time, and then it is quite robust system. You can use it as a backend, as I said, to multiple applications. But if you're looking for spatial capabilities, you can use this extension called as Postgres, which allows you to store the geographic objects along with the query capabilities, all using the power of SQL only. So PostGIS adds support for extra data types. If you remember from the definitions, it says support for user defined or spatial data types. So it allows you to store the geometry type, the geography type, even the rasters and other kinds of data can also be stored. Further, it also provides the various functions and operators, also the support for indexing on those types. So combining both Postgres and PostGIS is a quite robust spatial database system, and as I mentioned in the use case, you can use it for powering your creating your customized applications. It could also be used for powering your mobile-based application and also the web-based application. Another open source alternative for spatial database is the Spatialite. Now this is an extender to the SQLite database, which allows full capabilities of spatial querying using again the SQL language. Now good thing about this Spatialite is because it is based on SQLite, which is primarily simple and lightweight. There is no need for installation, there is no need for configuration. There is no it is just a simple file that you can put it, very lightweight. However, support all the standard SQL implementation. Unlike a Postgres and PostGIS system, which are primarily the client and server based follow the client and server based architecture, here it is more like a single file that is sitting on the system that you can use for storing the data. So the whole database resides in a single file, and then it becomes easy to move this file across from one system to another. And since it works around multiple platform, it is a cross platform, so you can move it across from one machine to the another. So unlike as I said, the Postgres and PostGIS, which has to be installed, a server application is running or a service is running for looking for answering a request for the client, it is completely no installation required and no configuration as such. So we can also say that SQLite with the Spatialite is it's similar to like your Postgres plus Postgres. So for your single user, or if you want to store data on a desktop or a standalone environment, so this is a good option wherein you can store the data, which is also easy to move across from one platform to another, and there are no installation and configuration kinds of issues, and you can store unlimited kind of data. Size issues are also not available. The third popular example is the MySQL. Now MySQL is one of the very popular example of a database system. People generally who are working on a web-based application use it under the LAMP stack, which stand for Linux, Apache, MySQL and PHP, which these are the four kind of stack that people generally use for developing the web-based applications. But it also supports the spatial extension, wherein It allows the storage for the spatial data types, also the functions and manipulations, along with indexing and other kinds of supports are also there. So if you're looking for creating a geo-enabled applications and you are already following a LAMP stack and you don't want to move it from, let's say, MySQL to a Postgres, you can still go ahead and use the MySQL system because it also supports the spatial extensions. So it supports the geometry type, the point, line string, the polygon, along with multi-point, multi-line, multi-polygon. Even the geometry collection could also be stored. Now all these open source softwares also provide a lot of functions. So maybe we can say that compared to a Postgres, MySQL will have a limited function capabilities, but it do provide functions to create geometries that could be in a well-known text or a well-known binary, or some kind of internal format is also supported. Now those functions also allow to convert geometries between the formats. So from one format to another, these are possible. Similarly, they provide function for both qualitative and quantitative properties of geometry. We can get the centroid, the area, and so on. We can also use the spatial topological functions to check with the relationship between one to the another. And we can also create new geometries from the existing one. So as I was mentioning, these spatial database system can serve as a backend engine that could power your various applications wherein the task of the data management queries capability could be delegated to the database, and your UI can becomes as a client to send and request across, let's say, a desktop, internet or internet environment to the backend system. So having talked about and given few examples of the free and open source softwares, now there are others under these categories like Ingress. Also, let's say we talk about drill, and also under the big data kind of a system, there are further which also supports the capabilities of spatial data. Now let's also talk about and maybe try to understand here how these kind of system works. And here I'm taking an example of Postgres and PostGIS for give you a glimpse of, or let's say a kind of feel of how we generally work across and use such system for storage, for management and retrieval, all using the SQL query. So we can think in terms of Postgres and PostGIS primarily from a client and server model, where the data could be stored inside a Postgres and PostGIS, and then we can use any client. So it could be our GIS as a client, wherein the data could be stored here, and then we can connect to the backend system, fire few queries, view the result, which could be visualized inside the QGIS. Or we could also use the database provided, let's say the clients, which could be a GUI based client like pgadmin in the case of Postgres, or it could also be PSQL, which is a command line interface. But since the data is let's say hosted across the internet or an internet, first we need to establish the connection by providing the necessary credential, which could be username and password, along with the, let's say, the IP address or the domain on which the database is running, and also the port on which it is listening for the request. Now, just a brief on the structured query language. So those let's say the learners who are following this topic, maybe if you just want to revise or learn a little bit more on the structured query language, so I have put few slides here. So structured query language is a declarative language which is used for, let's say, data retrieval and manipulation from the DBMS perspective. There are three types of SQL language, or we can categorize of three types. One is on the data definition part, also called as a DDL. As the name suggests, they are primarily related to creating of the database, or creating of the relations or a table, indexes, etc. Second is a DML, also called as data manipulation language, and as the name suggests, manipulation. So we, once our relation or a table is created, we use this category of syntax for inserting, updating or deleting the rows or tuples from the relations. And they are also used for retrieval of the query using the select statement, which is also the focus for this topic. The third category is the data control language, and this is primarily deals with the rights, the security permissions, so that the desired people should be able to handle or access only that part of the data. In a traditional relation system, the data is organized in the forms of rows and columns. So this table is also called as relation in the relation database management system. Individual rows are called as tuples, and then we have the concept of attributes. There is also a concept of a domain which talks about the permissible list of values that are allowed. For example, for the land use suitability, it could be medium suitable, high suitable, large suitable, and so on. So primary kind of constraint that we have defined into those columns. So if those constraints are violated, then the system will not allow the tuple or the row to be inserted inside the relation or the table. Right. So our focus, as I said, is more on the select statement, which comes under the data manipulation language, which allows us to retrieve the rows in response to the query. And general syntax is something like this, which is select is a keyword. The columns from these relations that we are interested, suppose say polygon ID and land cover. So which columns we want to retrieve from this table. So select, as I said, is a keyword. Column names will come here, or we can also use a star, which means all the columns. From again is a keyword followed by the name of the relation or a table. So let's say if this table is our polygon table, then it will be select star from polygon. However, we can also filter instead of seeing all the records or all the tuples, we can also do filter based on certain condition, where this where clause comes into the picture. So after the where clause, we need to provide the predicate or the condition based on which the filtering can be done. Now we can use the various relation and the logical operators like and or not, or greater than, equal to, less than equal to, some like kind of a things for pattern matching are all possible here. So general syntax is select the columns from the table where certain conditions are satisfied. However, there are more clauses, like we can also group based on the column, and then we can also filter based on the group. Now one thing to remember is that having works with the group. So if we are looking for filtering after we have done a grouping or an aggregation, we can use the having clause. All right. Before we move to the spatial query, let us discuss few examples of the query, so that you will be able to follow up also in the later slide when we talk about the spatial queries. Assuming that we have a book table having the book ID, the price, the author, and so on, and then we want to find out those books where the price is between, let's say, 100 rupees to 1000 rupees. Now again, if I go back to the syntax, it is like select columns from table where the condition is met. So in order to write this, what we can say is select is a keyword. We say select star, which means all the columns from the table. The name of the table is book, and then since we are looking only for those books where the price is between 100 to 1000, and as I said, after the where clause we can write the predicate, which in this case we are making use of relational and logical operators to tell the system that we want the price between 100 and 1000 with inclusive both 100 and 1000. So we are making use of the greater than equal to operator and less than equal to operator along with an and operator. The reason we are using and is because both the condition has to be satisfied. So again, on the syntax part is selecting columns from table and the predicate. And as I said, the predicate could be a simple expression or a complex expression. Let's say if you're only looking for price greater than 100, then we don't need to write this. But if you're looking for within this range, so this is one way of writing it. There are obviously other ways of writing it. We can also use the between clause, but here we just want to simplify for our users or learners. Now the other thing that we can also do is we can Also join multiple tables together. Assume that there is a book table which contains the information about the books like book title, ISBN number and other details, and the book author details, because one book could have multiple authors, are put under the separate table. Now suppose we want to find out for each book the number of authors. Now we know that book is one table and book author is another table. So there is a book table and second table is the book author table. So this is the author table and this is the book table. So for each book it will contain multiple authors. Now in order to answer this, because the information is there in two different tables, what we can do is we can use the join operator to join these two together based on the common ID or a common column, which in this case is the ISBN number. Right. So instead of starting from the select statement, I will start from the from statement and then I will come back to the select statement to tell you how we are writing this clauses. Now we know that the information is coming from the two tables. So obviously, unlike in the first query, there has to be two tables, which is from book, comma, book author. The second thing is we also need to join them, and then for join again we are using a where clause, but the join condition is where the ISBN number value column in the book table matches with the ISBN value in the book author table. So this is our join condition. Now since we are looking for books and the number of authors, so what we also need to do is we need to group by the title, because as I said, for each book there could be multiple authors. Hence we use the group by clause to aggregate the values based on the book title. Once we have done the grouping, now coming back to the select statement, then we can retrieve book.title, which gives us the one title because we are grouping by the title. And then I'm using a function called count, which basically gives the number of records, or let's say number of tuples per group based on the book title. Now one more thing that you will be wondering is I'm using as and title. So this is called as an alias. So instead of displaying onto the result like book.title or count star, I'm giving them a alias saying represent book.title as title. So in the output, let's say the records that we'll be getting, so the table or the column name will be title and authors. So this also allows you to join the tables based on the common attribute, which in this case is the ISBN number. There is also a concept of subquery, wherein the output of the one query could serve the outside query, and we can nest that across multiple levels. Let's take an example. Suppose you want to retrieve the books where the prices are less than the average price of the books in the books table. So first we need to find out what is the average price of all the books in the books table. So what we can do is we can make use of this subquery where this select average price from book will give us the average price of all the books in the books table. Let's say this comes across to be 1000 rupees, just for example. Now if you read this statement, select ISBN, title, the price from the book where price is less than 1000 ordered by the title. So basically what has happened here in this subquery, which is giving us the average price, becomes as the input to our outside query, wherein we are using it against a predicate to get only the prices less than the average price. So basically you can also think that the output of this will be, so the output of this will be used as the input for this query, which is price less than the average price of the number. Now one of the other clause that I have not mentioned is called as an order by. As the name suggests, we want the book to be ordered by the title, alphabetical order. So we can also do order by ascending order and also the descending order. So subquery is sometimes very useful for when we are looking for some information from our inside query or a subquery that we can pass it to the outside query for further usage. Right. Now there are other important SQL commands. These are mostly from, as I said, the data definition part, like creating of the database, creating of the table, changing the structure of the table like alter table, or changing the database like alter database, dropping the table completely like drop table, or removing the tuples from the table like truncate table. So there are a series of commands. But for this we are focusing more on the DML part, specifically on the select query. So having learned some maybe, or let's say, a revision of the SQL part for some of the learners, now let's get into the process of creating a spatial database. And in this here I'm taking example of a Postgres. So the most of the database systems will provide you some of the front end. So that could be a command line, like in case of Postgres as PSQL, or could be a graphical user interface called as a PG-admin. So this as I said, Postgres is available multiple platforms, so you can install it on Windows, Linux, Mac, and etc. So this PG-admin will come as one of the utility installed on your system. So if we just search for the PG-admin start, it will open in the browser, the default browser. The database here that I'm showing will be differing depending on the system, because in our case I have created some other databases also, whereas you will only get one of the trees, and when only the Postgres will be mentioned. Now GUI provides a good let's say easy convenience to create, so that you don't need to remember the SQL syntaxes per se, but whatever steps you can do in PG-admin, let's say graphical user interface, you can do it in also in the PSQL also. So the first step in any of the system is to create our own database. So we are segregating the data to be organized in a separate kind of a database. To go about it, what we need to do is right click on the database tab, as I mentioned it here, and in the pop-up window that comes, we need to select the database. Once we do that, a new pop-up window will come, wherein we need to enter the name of the database along with the some comments what we want we can write on that. So again, just to recap, the right click on the database, choose create and database, so it will open a window, and then you can enter the database names and some comments. So if you just click on the save, it will create a non-spatial database. But since we are looking for creating a spatial database, again there are options. So I will give you two options of working here. So instead of clicking save directly, go to the definition tab, and there are certain templates provided. For example, in Postgres, if you are using the latest version, so there will be PostGIS underscore 30 underscore sample. So the aim is to tell the system that we want to create a new database based on using this as a template. So basically you will get all those capabilities of the let's suppose the as function views all coming under if you follow this template. So basically once you do this and click on save, you'll see that the tables are populated, and also you can see some views have also come. So once you have done that, click on the save button and these are populated, you can be sure that this is now your spatial database along with the population of the functions. You can also check this function or this select statement you can write under the query tab to further verify the PostGIS version that you have installed. So earlier was one of the ways. The second, as I said, is we could also use, since I talk about that Postgres is a normal DBMS, we can enable the extensions to support the spatial data. So we can also follow the same steps, wherein we create the database just like by right clicking and opening the window and saying giving some name, and then we can also enable the extension. So under there is an extension tab, we can go there and we can also enable the extensions, or we can also go to the query tool and write this statement like create extension Postgres, and if we can click on the execute button, so it will follow the same process and your views, tables and functions will be populated. So you can follow either of the two approaches to work. Only thing to note is that your PostGIS template should be disconnected if you are creating based on certain template, otherwise say it is already opened. That thing you can please note. Now, as I was mentioning that once you have done these steps, the various metadata tables will be populated. Some are views also. One of the popular, or should I say, very important table here is the spatial references, which contains the various kind of spatial reference system information in this table. Now, there are two views which are primarily read only, which contains an entry for all the geometry columns that are present in the data. So primarily in Postgres, there are two types of, let's say, vector types that are available. One is the geometry, one is the geography. So geography is primarily by default assumes the coordinate system as 4326 or a geographical latitude and longitude, but the output comes in the form of metric. So if you're working for the whole globe region where the data is already in a latitude longitude format, you can go ahead and use the geography columns. But we are looking for projected area, you want to work on smaller region, then you can, or some other projection systems, then you can go and use the geometry type. So these are the basic two differences. These are the differences between the geometry and the geography type. Hence there are the two different views. For example, if you create a table wherein you are storing a geography type, so the record goes under this view, geography column views. If you are creating a table with the geometry column, let's say Cartesian, where you're not working at the whole globe or 4326 kind of a projection or a geographic latitude longitude, it comes under the geometry column. So as I mentioned during the the previous, when you're discussing about the functionality, so all those open source, all the proprietary SDMS systems provide various functions. Apart from the storage function, they also provide the let's say the retrieval function, the geometry editor function, the output, and important for the analysis perspective is the spatial relationship and the measurement functions. So I will cover the few of the important functions, and then we'll also discuss some of the examples queries. So to construct the let's say, or insert the geometry inside the function, since we can't directly put the geometry inside the tables, because in Postgres is generally stored in the form of an hexadecimal. So Postgres provides us functions like geom from text or geog from text, depending on the type of either geography type or a geometry type, where the objective is to take a textual representation of geometry that could be point, longitude, latitude, or x and y, or a line, point 1, point 2, point 3, point 4, or a polygon, again the points with the first point and the last point are same, and take this textual representation in a well-known text format and convert them into the actual let's say the geometry which is stored in the form of hexadecimal. Now just one thing to note is that all the functions in the PostGIS and also maybe mostly under the MySQL, they will be preceded by ST, which stands for spatial type. So you'll see that all the functions are preceded by ST underscore. So once we have created the geometry, we can also retrieve the geometry back, because sometimes we want to know the longitude, the latitude, or given a line, we can find the first point and the last point. And as this query and the below is mentioning that, we can select the name, also the starting point of the geometry, the ending point of the geometry from the lines table. There is also a function that is uses st underscore as text, because remember that st underscore start point will again give you a point in a hexadecimal kind of representation. But to convert it back to your textual representation, we can use a function called st underscore as text. So this will convert the geometry to the textual representation. So we can know that point x and y, or longitude and the latitude. So important thing here is, if you see that there are a series of functions that we can make use of for data storage and manipulation. Similarly, for retrieving the data, as I was mentioning, there is an st underscore as text, which gives you a textual representation of the of the geometry. Similarly, there is a binary representation that we can also have a look. Further, there are other output functions. Suppose I want to retrieve the data that I have stored in a GeoJSON format, or a KML format, or a GML format. Again, those output functions are available. And these are very useful, especially when you want to convert the geometry into a format that is compatible to your let's say the application that you are building. Suppose for your web application you want the data to be in GeoJSON, so that could be represented onto the client side, so you can convert them using this function and send it across to the client for visualization or adding it on the top of a base map. So those capabilities could be built in. Now these are the functions which comes under the relationship and measurement, which are very useful when we talk about from the analysis perspective. So these are like contains, within, and these are primarily your topological relationship functions that you study in a typical, in a GIS kind of module, about the relationship between one feature and another. So all those, if you can see it here, that these capabilities are offered from a underlying DB engine, wherein you can perform those operations and then power your various kinds of applications. That could be mobile, desktop, or other custom built applications. Similarly, PostGIS also provides some functions like measurement functions. So given a geometry, we can find the area, let's say for the polygon, or a polygon we can get the centroid or distance between two geometries, the length of the line, the perimeter of an area or a polygon could be extracted. Again, the output depends, or the units depends on the the actual, let's say the coordinate system on which the underlying data is being stored. So again, there are a lot of measurement function that could be used for computing the area, perimeter, etc. Now here I will take few examples. First, to create a simple spatial table where we just want to store points, and then we'll build it up for the spatial queries. So the first is to create a table. So we can use the create table statement, which is create table, the name of the table. In this case, it's a global points. And the table will have attributes, as I mentioned in the previous slide. So here we have attributes like ID, named, and since we want to also store a point, so we are given the name for that column as location and type as geography, and we want to store the point. Since we want to store the point in geographic latitude, longitude, the SRID, which is the term used in Postgres to refer to the projection system, is 4326, which stands for geographical latitude and longitude. Now for the name, we have given as a character type. For the ID, we want to make it as an auto number along with the primary key. So we have put it as a serial, which basically gives us an auto number, creates a sequence by default, and we are making it as a primary key, which means that this could not have a repeated value. So if you run this create table statement in a PSQL or under the pgadmin, it will create a table. So that table will be added into your table list under the schema. Further, it will also be registered under the geographic column view. So if you just go under the view, right click, say view data, you will see that global points has been entered. And these are very important, especially when you want to use some GIS client to access the data. So this primarily differentiate which are the tables which are spatial tables versus the non-spatial tables. Right, so our table is created. Now how to insert the value into the table? So as I said, under the DML, one of the statement is the insert statement, which allows us to insert the data into the table row by row. Now, as I mentioned, it is easy to put a value under the name category because this is a text. So we can put text under quotes, say values is text. But how should we put the geometry information inside the table? So this is where I explained in the previous slide that there are a series of constructor functions like st underscore geography from text, which primarily takes a textual representation. If you see here, it is a point function containing the, let's say the x and the y value along with the SRID value, and we are saying convert this into the equivalent or the geography type, which is let's say the hexadecimal values that the system stores. So if I just interpret this line, it is like insert into the table. So this is a standard insert into tables. Since you only want to insert the values under the name column and the location column, because ID we have automatically made as an auto number, so we don't need to fill that values, followed by the keyword called values. Now what we need to do is this town will go under the name column, and the output of this function will go under the location column as a hexadecimal values. And all the SQL statements will end with the semicolon. Similarly, we can now write multiple insert statement to insert multiple points, let's say town, forest, or some city name like that. So the first values goes under the first column. The output for this function, which will be the geometry representation or the geography representation, goes under the location column. So the steps is 2. So first create a table, but unlike a normal non-spatial table, you will also create a column which can store the geometry. In this case, I am storing the geography type of a type point with the projection system as geographic latitude longitude, represented by the keyword as 4326. Now where we can know about these things is, as I said, you can refer to the spatial references tables. You can query on them, which contains these SRIDs for against all the possible projection systems. And then you can insert the data into this table using the insert statement, which is insert into the table followed by the columns and the value stack. So we have to ensure that if we are giving 2 columns, then there should be 2 values after the values, otherwise it will give you an error. So again, the first values goes under the name column because it's a text we are putting in the single quote, and then for putting the geography type, for storing our spatial objects, we are using the constructor function called as the geography constructor using a textual representation known as st_geography from text. Now you don't need to remember these functions by heart because if you use it quite often, you will be remembering it. But as I said, Postgres has a very good documentation, so you can fall back on the documentation to know about the proper syntax of the function, the parameter required, the order, and so on. So once the points are inserted, then what we can do is we can retrieve using the select statement, which is select name, comma location from the points. As I said, this location is stored as a hexadecimal number. So in order to see it as a textual representation, in the next query, we are using one more function called as st_as_text. So st_as_text takes a parameter like the name of the geometry column, which in this case is location, and now you can see that this gives us a textual representation of the geometry or the spatial objects. In this case, it is a point that we have stored. So London point X and Y, and then so on. So this is how we can create a simple, let's say we want to store some GPS points or some other points that we want to store. But this Postgres also provides a utility wherein suppose you already have a data in a shapefile, and then it provides a importer utility wherein the shapefiles could be directly imported into using these utilities, which will be in turn converted to a tables inside your database system. Only thing is this again you can start by using the utility available once you install the software. If you fire this utility, it will open. First you need to establish the connection by entering the username, the password, the host and the port along with the database that you want to connect. Once you have established the connection, you can add your shapefiles. By default, the name of the table will be the name of the file, but you can use these options for editing and changing. Important thing, the SRID. One way, as I said, is you can use the spatial references table, or you can also make use of the QGIS. You can open the shapefile in QGIS, go under the layer properties option, and in the properties you can get the SRID for that particular the projection system that you are using, and you can fill that in here. Click on the import button and it will be directly be imported into your database. So this is an example of a pgadmin GUI wherein you can write the query under the query editor. So that comes under the tools, or you can also use these buttons to fire that same thing. You can click on this execute button and you can see the results here. Now from the pgadmin 4 onwards, it also provides you a geometrical viewer. So if you click on this I button, you can see that it will also show your points with the under the geometry view. and then there are series of background maps that are available. So if you are connected to the internet, then you can make use of these maps, change them, and you can see the map, somewhat visualization you can do. As I said, because this is a DBMS system, this is not a complete GIS system with all the visualization capability, but basic visualizations are provided. Now, having talked about this, now I will just discuss few of the spatial queries. So just to acquainted with how to write certain queries. So for this, I'm taking two tables. One is the roads table and one is the municipality table. So roads is a line feature with three columns like ID, name, and the geometry column. Municipality is a polygon having four columns: ID, code, the name of the municipality, and again the geometry being stored inside the geom column. So we'll take this as a base and see some few simple queries. So roads and the municipality. Let's see the first query, which is the we want to find out the total length of the roads expressed in kilometers. Now again, whatever we have learned so far with the select statement, so we need to say select. Maybe I will come back to this expression later, but we need to select certain things from the table. But what we know is that I have to select certain columns from the road. So this part is clear, the select and the from roads. Now what we are looking for is the total length of the roads. And there is a function called st_length, which provided the attribute or the geometry column will give you the length for each and every tuple or a record or a roads in the table. Now what we can do is we can make use of the aggregate function like sum. So if I say sum the length of the roads will give me an aggregate value of the length of all the roads in the roads table. And if I divide this by 1000, that will convert it into the kilometers. Hence we are making use of this alias like as kilometer roads. So just to again maybe tell one more time is we are selecting from the roads, since we want to select the sum of the roads or the total length. So we are making function use of the aggregate function called sum, passing it the length function with the parameter of geometry column and converting this sum to in kilometers by dividing the results by 1000. So if you just use the st_length the geom from roads, it will give you the length of the roads for all the roads in kilometers. But the moment I put an aggregate function as sum, so it will just combine them and give a single value which you can represent in the kilometer by dividing the results by 1000. Similarly, we can also use the area function to find out the size of the city, particular city from a municipality. So again, if you look at this, if you remember the syntax and then if you relate it to this query, it is like selecting the area from this municipality where the name of the municipality is the particular one we are looking for, which is Prince George. And again, what we are doing is we want to convert to hectares, so we are dividing by 10,000, given alias as hectares to represent it. So instead of the length function, here we are making use of the area function. So again, if you see, the query is the same, only the let's say we are mixing and matching both the non-spatial along with the spatial function, like the area and the rest statement still follows the same SQL. A variation of this could be we want to update the existing area field with the area in hectares. So then I can make use of the update statement, which again comes under the DML category. Update table name, set area equal to the new area. So we have a column, let's say the area column, which contains the area value for each municipality in meters square, let's say, and then we want to convert it to the hectares. So what we do is we say use the function update municipality. Set is a keyword, the field we want to update like area to the new area. So to replace with the new area, we are using the function called stArea, passing the parameter which is the name of the geometry column and dividing by 10,000 because we want to store the values in hectares. Let's see this the third query. What we want to find out is the municipality with the largest area. Now we know that there is a function called ST area, so which gives us the area for each municipality. So if I can find out the for each municipality the area, and somehow if I display it in the descending order of the area size and select the first record, I should be able to get the municipality with the largest area. So this is what this query does. So it's use the select statement, select the name of the municipality along with the area. This is an alias as hectares from the table called municipality. Here if you see it now closely that I am ordering by the hectares because this was an alias names, but we are ordering in the descending order. So if I take the name of the municipality and the area of his municipality and then sort them by the area or the hectares field, in the descending order, the largest municipality will come on the top and say, give me only the first record. So this is how it can be done. But this somehow will not work if there are, let's suppose there are two municipalities with the same area. Right. So in that case, you can make use of the subquery that I have discussed in my previous slides. So you can use the subquery for finding the, let's say the maximum area, and then you can use it as an input for our previous query. Similarly, you can also find out the parameter of a particular municipality, in this case the Vancouver, and then so slowly we can also use, let's say, the spatial function like distance, intersection and so on to also perform some spatial queries. One example is given here is, let's say we want to find municipalities that are a distance from the roads. So this is like making a buffer around the roads of a particular distance and checking whether they are within that zones. So one good function is the std within, which combines the buffer along with the comparison of within. It takes three arguments, which is the first geometry, the second geometry and the radius, or specifying the distance that we want to check. And this is a very good function when you are looking for containment with reference to a buffer. And the query given below primarily does that. The reason we are using a distinct in front of our name is because it is possible that the same road may be a distance away from, or municipality may be a distance away from the multiple roads. So the distinct will give only the unique names. Now one more thing, if you can notice, is here I am also using an alias for roads as R and municipality as M, just to shorten the query kind of a writing. Rest is still the same. We are making use of the d within function here, passing the parameter like the road geometry column, the municipality geometry column and the distance as 200 meters. Now this within primarily returns a boolean value true and false, which is being checked. So all those geometries, roads which are distance of 200 meters will be returned. Sorry, the municipalities will be returned, rest will not be returned based on this query. So again, as I said, this is a very good function where you are looking for buffer along with the contain or the checking whether one is within the other, all in the inside the single query. Now sometimes we also want to find out whether, suppose in this case, the neighbors of a particular municipality. So this is a case of a self join. If you see here, I am writing the same municipality two times with giving alias as C1 and C2 and using the using the condition as touches, which gives us the containment part. Right, and then other thing is we can also make use of these queries also accessing from our GIS system. So suppose QGIS provides a plugin like a DB plugin wherein you can write those queries and you can also get the records. So which means instead of using pgadmin for writing queries, you can still use your traditional GIS system for fetching the queries, and then you can also visualize the results inside it also. Now there are other functions that will be very useful, like intersect and intersection. Suppose you are looking for whether the two geometries are intersecting with one another. So there are two functions. One is a intersects, which is only giving you a true and false, a check for a intersection, whereas the st_intersection is giving you the common area. And this is, again, you can use it for various applications. I will give you one simple example, which is in this case is given a, let's say, flood hazard map in a web-based system. We allow the user to draw an area of interest. The user draws the area of interest, and then based on whatever he has drawn, we can use the power of this Postgres system and then compute at the backend based on this area and the flood hazard map. What portion of the area has come under the high, low, medium, and very high category. All on the fly could be done. So like this, we can develop multiple applications that could be quite useful uh, for as I said, for powering your mobile, desktop, and other kinds of applications. So now one more thing is how you can go about doing or working on such system. Is very good application is OSGeo Live, which comes with the pre-installed options of the various software, so you don't need to install them. It comes as a download bootable DVD drive. You can also burn it on your pen drive, or a virtual machine option is also available, where you can just download as a virtual machine, use some VirtualBox environment, all those complete, let's say, the open source softwares from various types from desktop. And from my perspective, the databases comes pre-installed, so you don't need to install anything. So you can try them just by using this simple installer utility. And there are good quick start guides also available. So how to start, again the good documentation somewhat is also given here, along with the data sets are also provided. So this is a good option if you want to try different softwares to see which one how they are working, instead of first trying to download, install, and starting from the scratch. So this is a good way, fast track way to start the, let's say, the FOSS journey. So with this I will be stopping it here. So in this session we talk about the FOSS various offerings under the spatial database system. We understood the few fundamentals of database system, the DBMS, the definition of spatial database systems, the characteristics, the various FOSS offerings. We talked about MySQL, Spatialite, and Postgres, and also I have given you a glimpse of how we actually work in a spatial database system by using the spatial queries, using SQL language for interacting with the databases. So I will stop it here and I will wait for your questions.